Welcome. In this session, I'd like to talk about probabilities, how we measure them, how we use them, and what they mean for the future. I'd also like to talk about some tools that come out of the toolbox in probability. So let's start with a very simple definition of what a probability is. We live in a world where there are very few certainties. Put simply, we're uncertain about most things. A probability measures the likelihood of an outcome occurring when we're uncertain. So let's set the limits on probability. A probability for something happening can range from 0 to 1. When the probability is 0, it's impossible. This event can never happen. When it's 1, it's certain to happen. Life gets interesting between those two numbers. If your probability of something happening exceeds 50% and keeps getting higher, that event is clearly more likely to happen. When the probability of something happening drops below 50% and gets low, it's less likely to happen. If there's a 50% chance of an event happening, it's called even odds. You see, why does it even matter in investing in finance? In investing in finance, we're faced with the task of estimating probabilities for all kinds of events. Some are discrete. Let me give you two examples. Will my company go bankrupt in the next 5 years? That's a discrete event. You're either bankrupt or you're not. I can estimate a probability. In fact, banks and ratings agencies try to do this all the time. Or I might wonder whether a company I'm invested in is going to become the target of an acquisition. Why? Because I make money off acquisition. So it's good for me when my company is acquired by another company. I can estimate the probability of that happening. Discrete event. You're either taken over or you're not. Alternatively, I can estimate the probability of something that's continuous. And here's how it would work out. Let's suppose you have a company that has $500 million in earnings. And I'm curious about what the likelihood is that this company will make more than $1 billion in earnings sometime over the next 5 years. I can estimate a probability. Alternatively, I can take the same company and say, what is the likelihood that my company will have negative earnings or report a loss sometime over the next 5 years? So with that set up, let's think about two views of probability. There's one view which is, I think, a fairly rigid view of probability. It's called the frequentist view. That probability measures the frequency with which an event will happen if it's repeated many times. Again, I'll give you an example which I've used multiple times before. Coin tosses. I can repeat coin tosses as many times as I want, 100,000. In fact, I can get a computer to keep flipping coins millions of times. In the frequentist view of probability, ultimately the truth will win out, because if you repeat an event enough times, at some point in time, you will be able to estimate the likelihood of a head or a tail. So if you have a fair coin and I repeat this toss tens of thousands of times, eventually I'm going to end up at 50-50. The nice thing about the frequentist view is there's no his view, her view, or their view. Ultimately, all views get subsumed by the truth. There is a truth and it will come out once you've repeated the event enough times. Alternatively, there's what's called the subjectivist view. It's also called the Bayesian view, and I'll come back and talk a little bit about what Bayesian views bring to statistics. But in the subjectivist view, you attach a likelihood to something happening even though you cannot repeat it multiple times. In almost everything we do in investing in finance, we don't get the luxury of repeating an event tens of thousands of times. So if you're an investor, you invest in a company, your lifetime is limited. You don't get to do this over and over again tens of thousands of times. But you can still attach a probability that you will make money on a stock sometime over the next 20 years. But because there is no eventual truth, repeating of event tens of thousands of times, the subjectivist view, unlike the frequentist view, rational individuals can disagree about what the probability of something happening is. So as an example, think about what we think will happen to the stock market over the next year. I can bring everything I know about stocks and give you my assessment, but it's still my assessment. And you can bring everything you know and give your assessment, but it's still your assessment. because neither of us is going to be around long enough to see this play out over and over and over again. There's only one next year. You can't tell me that one view is right and the other is wrong. One could be less wrong and the other could be less right. But that's basically all we can do. In investing in finance, it's the subjectivist view of probability that we'll draw on far more frequently. Now, staying on the theme of probabilities, there are two other versions of probabilities that you might run into. The first is called a cumulative probability, which is the likelihood of a series of outcomes happening. So to compute a cumulative probability, you have to define each event in the sequence, estimate the probability of the events, and the events have to be independent of each other. So if you ask me what the probability is that an investor who picks stocks randomly will beat the market 10 years in a row, I can estimate that probability. Because even though he or she has only a 50-50 chance of beating the market, I can estimate a probability, and it's not going to be zero, that he can win 10 years in a row purely based on luck. It's one of the reasons it's so difficult to disprove the notion that markets are efficient. Just because some investors beat the market for extended periods does not mean that they found a magic way of winning or beating the market. A conditional probability measures the likelihood of something happening given that something else has happened. So as an example, if you ask me to estimate the probability the market will go up tomorrow, and you tell me that today the market was up strongly, I can estimate a conditional probability saying, hey, given that the market was up strongly today, what's the chance of the market being up tomorrow? You might say it's still 50-50, but that's a function that only the data can answer, or a question only the data can answer. Cumulative and conditional probabilities. Now, when you work with probabilities, there are a few simple rules that govern probability. The first is the probability of an event happening is always bounded, which is just a fancy way of saying it's got to be a number between 0 and 1. You can't tell me the probability of an event happening is 120% or minus 20%. If I give you the entire universe of outcomes, the sum of the probabilities of the outcomes has to be equal to 1. In other words, everything that happens is in front of you. If I add up those probabilities, it's got to equate to 1. If I give you the probability of something happening, let's say X, then the probability of X not happening has to be 1 minus the probability of X happening. So if I told you there's a 60% chance the market will be up tomorrow, then I'm telling you there's a 40% chance the market will not be up tomorrow. The general addition rule says that if you have two events, the probability of either X or Y happening, one of those two events happening, is the probability of X plus the probability of Y minus the probability of X and Y happening together. In other words, I can back into the chance that X or Y will happen by dealing with those probabilities. Let me give you an example. Let's suppose I'm interested in finding out what the probability is that both Google and Apple will be up tomorrow. What if I told you there's a 60% chance that Google will be up and there's a 65% chance that Apple will be up? If you just add the 60 and the 65 and say the probability that either Google or Apple will be up will be 125%, you can see it doesn't make sense. So you've already violated a rule of probability. You know what you're missing there? That the 50% of the time both Google and Apple are up. So if you want to estimate the probability that either Google or Apple will be up tomorrow, here's what you got to do. You got to take 60%, which is the probability that Google will be up, the 65% that Apple will be up, and then subtract out the 50% when the two are up together. You're going to end up with a 75% probability that either Google or Apple will be up. Of course, if they're mutually exclusive, then you can add up the probabilities. So if I tell you the likelihood of the Yankees winning is 50%, and then I tell you the chance that I will go out for dinner is 20%, then I ask you, what is the chance that I will either go out to dinner or see the Yankees win? Given that they're mutually exclusive, I'll say it's 50 plus 20, 70%. Finally, there's a rule called the multiplication rule, where I've asked you, what is the chance of both X and Y happening? Not X or Y, but X and Y. that Google and Apple will be up tomorrow, then the way you estimate it, if you have independent events, is you take the probability of X times the probability of Y. That won't work for Google and Apple, but it'll work for the Yankees and me going out to dinner. Given that they're independent, if you ask me what's the chance that both will happen, then I'm going to take 0.5, the chance the Yankees will win, plus 0.25, which is the chance I go out to dinner, and the product of those two will be the likelihood that I will both go out to dinner and see the Yankees win. If they're not independent, then I've got to estimate the probability of the first event happening, X, and then I have to estimate the conditional probability that Y will happen given that X has gone up. In the context of Google and Apple, I'll estimate the probability that Google will go up 60%. Then I'll estimate the probability that Apple will go up given that Google has gone up. That product is going to be that product will be the probability of both Google and Apple happening simultaneously. So let's talk a little bit about Thomas Bayes and what he brought to statistics. His most famous theorem says that the probability of an event occurring is conditioned on your prior knowledge of every variable related to that event. In effect, it's always a conditional probability. He was stating a truth, which is you almost never estimate the likelihood of something with a blank slate. You bring in your priors, what you already know, into that estimate. And since that knowledge or information is going to be different for different individuals, he stated another obvious, which is you can have a dozen people looking at the same event, and because they bring in different degrees of information and knowledge in the way they process that information, they can estimate different probabilities for the same event. Now, do you see why you can have 10,000 investors in a market all looking at financial statements and analyst reports, looking at the same stock, making very different judgments on the likelihood that that stock will go up? That's Bayes' theorem, that your priors will, whether you like them or not, affect the probability estimates you make of an event happening. In Bayesian inference, you go further. You say once you estimate a probability of an event happening, if new information comes in, you're going to update that probability. Again, let me make this specific to investing and finance. Let's say you invest in a company where you had great faith in the company's products, its management, you thought it was a great company, and you bought shares in the company. So Bayesian theorem led you to think that the likelihood that the stock will go up was high, therefore you invest in the stock. Then you get a news story that the CEO of the company has been indicted for fraud. Might that affect your probability? I would think it does. You've now received information that might lead you to rethink your priors. The new probability that you attach to this stock is a good investment is called your posterior estimate as opposed to your prior estimate. And it reflects the new information you've learned about the outcomes. Investing is a perfect place to think about Bayes playing with his rules, his theorems, and his inferences play out. We're constantly making judgments on events happening based on what we know, and we're constantly reassessing those properties based on new things we learn. So let's talk about some tools that come out of the process of probabilities. Remember the last sessions we talked about a regression. In a regression, you have a dependent variable that you try to explain with a bunch of independent variables. There's a subset of regressions. They're not called regression, they're called Probit and Logit models, where what you're doing looks a lot like a regression. There are independent variables, but the big difference is your dependent variable, rather than being a continuous variable that you're trying to explain, like stock returns or PE ratios, can take on the value of either 0 or 1. Now, I'm going to give you a couple of examples so you can see this play out. But in a Probit model, you're trying to estimate the probability of something happening from this equation. It looks like, as I said, a regression equation, but the output will take the form of a number between 0 and 1, and therefore can be read as a probability. For instance, we talked about how when you're an investor, you might care about whether your company is going to be targeted for an acquisition. And maybe some of the things you might look at to make that judgment might be the size of the company, how well its stock has done, what kind of returns it made as returns on equity or accounting returns. So you have a hypothesis about what drives hostile acquisitions. You might decide to do a Probit where those variables now become your independent variables and you predict whether your company will be the target of a hostile acquisition. A Logit model is very similar to a Probit model. In fact, it's a little inside statistics, but kind of hang in there. The only difference between the two, because they both estimate probabilities, is the way they convert your output. Because when you put these independent variables and you predict a number, that number doesn't look like a probability. So both Probits and Logits convert the prediction you get into a number that looks like a probability. But the way they get there is a little different. The Probit model assumes a normal distribution. It uses a normal distribution to convert your predictions into a probability. The Logit model uses what's called a logistic distribution. Is one better than the other? I mean, this debate can go on in statistics, but the reality is both Probit models and Logit models are designed to forecast whether a discrete outcome will happen or not happen. In the applied session, we'll talk a little bit more about this. But one of the challenges we've always faced in business, especially lenders have faced this, people who buy bonds have faced, is the likelihood that your company will default or go bankrupt. So for a long time, it's been an entirely subjective process until data started getting collected to a point where you could use the data to make better predictions of bankruptcy. I'm going to give you an example of a Logit model that's been around a long time to do this. But here's what Logit models were used for to predict bankruptcy. Here's how Logit models were used to predict bankruptcy. So let's say you go back 10 years. You collect every publicly traded firm in the market 10 years ago, in whatever market you're interested in. You then look at how many of these firms went bankrupt and how many survived. So if you start with 10,000 firms, maybe 500 went bankrupt and 9,500 survived for the 10 years. Here's what you do. For the 500 that went bankrupt, you make your dependent variable 1. And for the 9,500 that survived, you make it 0. So if you survived, it's 0. If you went bankrupt, it's 1. So that becomes your dependent variable. Then you throw in the drivers of bankruptcy. You know what the level of earnings are, how volatile they are. In other words, you measure this for each of the 10,000 companies. The amount of debt they have, access to capital. So you throw in independent variables. Then you run a Logit. And when you're done, you're going to end up with an equation with the earnings level, the volatility, the debt level, all your independent variables. You plug the numbers into the independent variables, you'll come up with a predicted number that's between 0 and 1. Magical, right? You can then use the output to come up with a probability of bankruptcy. So in other words, you can come up with a number from the Logit that can yield a probability of bankruptcy. Here's a Probit model. Let's suppose you want to find out whether your company will become the target of a hostile acquisition. Again, you start with all firms, and this goes back to the issue of survivor bias. You don't want to start with the firms that are around now. You want to go back to the start of a period and look at all firms that are publicly traded. Then your dependent variable becomes whether the company was taken over or not taken over, whether it became the target of a hostile acquisition or not, 0, 1. The independent variables might reflect the things that you think drive hostile acquisitions: poor stock price performance, managers who don't own much shares, bad accounting returns. Again, you build a Probit model with those independent variables in. You plug the numbers in for your company, you can come up with a predicted probability of a hostile acquisition. I'm making a fairly complicated process more simplistic than it really is, but that's the end game you're playing. That's Logit and Probit models. A second place you're going to see probabilistic approaches come into play, what are called decision trees. A decision tree is a very useful way of modeling risk when it's sequential. Let me give you an example of sequential risk. You're a very young pharma company and you have a very promising drug to treat diabetes. The drug's just come out of R&D. But remember, you can't produce the drug for commercial use yet. You got to go through a 3-step FDA approval process. At each stage, you can get approved or not. If you don't get approved, that's the end of the game. So there's sequential risk at each stage. In a decision tree, you bring in this risk by first modeling the likelihood at each stage that you will pass or not pass, and what the outcome will be if you pass or not pass. And then you draw the decision tree. In fact, when you see decision trees, you'll see 3 types of nodes in decision trees. First are event or change nodes. Think of these as things you don't control. Karmic nodes, things that happen where probabilities will determine whether something good happens or bad happens. Those are event nodes. Then you have decision nodes. Here you control what to do next. So if you get a bad outcome, you can decide to keep going. That's a decision, or you can decide to stop. That's a decision node. Then every decision tree has an end node. When the uncertainty is played out, you get to that end node. That's why you get the final outcome. Event nodes, decision nodes, end nodes. In the applied portion of this session, you're going to see a decision tree, but that's the end game. Now, once you have a decision tree, you might say, what do I do with the decision tree? Again, until you see the actual numbers, it'll seem abstract, but with decision trees, what you try to do is roll back the decision tree. What you do is you start with the end nodes, which is the only node at which you know exactly what the outcome is, and using the probabilities and outcomes you've estimated for the earlier sections, you go back one step at a time. And at each step, you computed the expected value of each branch. And when you're done, you're going to get one expected value today that reflects the entire tree. In fact, you can make this more sophisticated. There's a time lag. You can bring in the time value of money. You can discount the payoffs. Basically, you can make decision trees as complicated as you want them to be, but it's designed to capture sequential risk. And one final probabilistic tool that you might end up using, especially in investing in business. Often in investing, you're faced with uncertainty about the future, and that uncertainty is often continuous. In other words, things can range from very bad to very good and lots of intermediate outcomes. But there are times when you can break these continuous outcomes into groups. A very good case, average case, bad case. Or if you're facing regulatory environments where you can get a really positive environment, a kind of neutral environment, a bad environment. In other words, scenario analysis is designed usually for macroeconomic uncertainties which can create very different outcomes. I'm going to give you the example of a valuation headed of EasyJet, which is a UK-based discount airline. In 2019, when Brexit was creating real uncertainty about what the future will deliver. We'll wait to see what those numbers look like, but there's 3 scenarios I looked at. Smooth Brexit, which at that time the probabilities were fairly low, kind of a rocky Brexit or no Brexit, and very different outcomes under each one. I know there are subset scenario analysis. Some of you might have run into what's called best case, worst case analysis. Best case analysis, you set every assumption at its best case. You compute what will happen if everything meets your best case scenario. Your worst case, you look at everything happening, which is what. I generally am not a great believer in best case, worst case, because here's what you generally find. Best case, your project or company or investment is going to be worth a lot. In your worst case, it's worth nothing. You actually learned very little. What I think makes more sense is to do plausible scenarios. That's why I use the Brexit example. Plausible scenarios where with each scenario you examine what will happen and then you compute the expected value under each scenario. In fact, in general, for scenario analysis to be most useful, I think you need to list scenarios to cover all possible outcomes. You have to estimate probabilities for the scenarios. You've got to complete your scenario analysis, but not only giving me the value under each scenario, but telling me an overall expected value. Otherwise, it becomes a way of covering your rear end because you do 100 different scenarios. Obviously, your numbers are going to range from really good to really bad. It's covering your rear end because no matter what happens there, one of those scenarios will cover it. Unfortunately, that's become part of the play in many analysts using scenario analysis. So I think there are places for scenario analysis, but we've got to be careful that it's not being used as a way of evading responsibility. I hope you found the session useful, and thank you very much for listening.